a review of special angles and trigonometric expressions, and we're going to look at the degrees, and we're also going to look at the radians of these special angles. So on the board I have two diagrams that have helped in the past on determining the special value angles for trigonometric expressions. If you remember, in order to create some of these special angles, we took a triangle. And it wasn't any special, it was a special triangle, it was an equilateral triangle, all of side length 2. And we chopped this up, and in chopping this up allowed us to do sine of certain angles and create exact values for those certain angles. If you remember to chop it up, here we go. We're going to chop this one up right here, and we'll chop this one up in the same way, and we'll look at the radians instead of the degrees. Okay, so you remember if it was an equilateral triangle, all the angles were 60. So this angle down here is 60. Now when I split it in half to create two right triangles, that leaves this being the hypotenuse of this right triangle. This is, say, the height, and this is half of this length right here. So this length right here is a 1. And then allowing that, we could say, knowing this hypotenuse length and this being 1, use the Pythagorean theorem and solve for this length, which we got as root 3. If you're not sure, make sure you plug those into the Pythagorean theorem and get a root 3 for that particular length. Now that we have all that, it allowed us to write down values. Let me get this 2 out of the way. It allowed us to write down values for like sine of 60. Okay, so just as an example, we'll do some examples in a minute, but sine of 60, if you remember, was equal to, now we've got SOHCAHTOA ingrained in our memory, that sine is opposite divided by hypotenuse. Therefore, in this triangle, we could use these nice numbers, or these low numbers, to fill in and always remember certain values. Okay, so sine being opposite of 60 would be root 3 over 2. So always, in an exact value, the sine of 60 is root 3 over 2. Now we could set this up similarly and look at, since we chopped that in half, that angle up there is 30, and we could look at the sine of 30. The sine of 30 would be its opposite, 1 over 2, or its hypotenuse, so 1 over 2. So sine of 30 is always a half. And we could set it up for tan in the same way, or look at all the different angles between 30 and 60. So this was the 30-60 triangle to help us remember those exact values. Now, similarly, we can chop this triangle up, but label its angles and radians. Okay, so similarly, this is going to be the same equilateral triangle, 2, 2 all the way around, and this will be a 2 down here. And since it's 60 in each angle, we remember if it's 60 degrees on each angle, in radians, 60, if we times that by that pi over 180, and simplify, 60 goes in there once, 60 goes in there 3 times, that's pi over 3. So this angle down here in radians is pi over 3. Now if I chop that up, that is 2 as the hypotenuse in this right triangle. That angle is pi over 3. We know that this length is root 3. Then similarly, I can write an expression for sine of pi over 3 and get an exact value. So sine of pi over 3 is opposite root 3 over the hypotenuse, 2. So sine of pi over 3 is the same as sine over 60. We're just now using radians. So that's the way we're going to chop that up. Now, let's complete the triangle by writing this angle in up here. Normally that angle was 30, so 30 as a radian would be 30 goes in there once, 30 goes in there 6 times left. This is pi over 6. You'll get to a point, if you practice this enough, that you will remember pi over 6 is always 30 and pi over 3. It'll be interchangeable. You'll just know when I say 60, that's the pi over 3 angle. And when I say 30, that's pi over 6. You won't have to do this conversion every time. But if you need to, that's the way you do it. Okay, so that triangle is set up for us to do the exact values. Let me label that as 1. We're going to do some examples in a minute. Now remember, there was a second diagram that allowed us to do the 45-degree special angles. And that came from the square. And if you remember, the squares, all the lengths in the square were 1. And we cut it into a diagonal. In the degrees, we said that this, since we cut it in a diagonal, that was 45 degrees. Again, using Pythagorean theorem, we would show that this is root 2. And then this is 45 degrees. Obviously, this is a right angle. And then I could figure out any trigonometric identity or trigonometric value from this one diagram. If I wanted, for example, tan of 45, then tan would be opposite over adjacent. That would be 1 over 1, which is just 1. So the exact value of tan over 45 is 1. Okay, in the radian format, we're going to do the exact same cut. We use the exact same triangle. If that's 1, that's 1, and this is root 2 as its length. We're just going to replace the angles in radian format. So 45, if I convert, 45 goes in there once and it goes in there 4 times. This is pi over 4. So this is pi over 4. And therefore this is pi over 4. And if I wanted to do sine of pi over 4, then I would go opposite over adjacent or hypotenuse. So this is 1 over root 2. So the exact value of sine of pi over 4 is 1 over root 2. So we're going to leave these diagrams set up. We will always, from now on, when we're doing these, we'll always be looking at our radians and not going back to degrees very often. So when I draw these diagrams, I will always draw the radian format. Okay, let's do a couple of examples here. Say I wanted to do part B, which was sine of 30. So that would correspond to this triangle over here in the degrees. And therefore sine of 30, this is just practice using our diagrams. Sine of 30 would be 1 over 2. By using that diagram, there's 30 opposite over hypotenuse. Let's look at another one. C would be sine of pi over 3. So pi over 3 is in our 30-60 triangle, or pi over 3, pi over 6 triangle. And therefore, pi over 3 is this angle, which corresponds to our 60 angle. And sometimes how I remember that is think about pi. Pi is big. If I divide it by 3, I get I don't get as a small a number as if I divide it by 6. Pi divided by 6 is smaller than pi divided by 3. So therefore, pi over 3 is the bigger number than this number here. This is the 60. This is the 30. Okay, so pi over 3 would be, sine of that would be opposite root 3 over hypotenuse 2. So this is root 3 over 2. Last example on this slide is cosecant of pi over 4. Pi over 4 corresponds to our square. Cosecant, if you remember, is the reciprocal of sine. So normally sine would be opposite over, right, we did this one, opposite over hypotenuse. Therefore this is hypotenuse over opposite. I'll write it out. And pi over 4 would be the opposite, the hypotenuse, which is root 2, over the opposite, which is 1, so therefore I'll leave it as root 2. So the exact value of cosecant of pi over 4 from that diagram is root 2.